We've described what a basic artificial neural network looks like, but how is it trained? And how do we train it effectively and efficiently? We'll try to answer those questions by discussing how neural networks are trained, the hyperparameters of neural networks, problems you'll face when training neural networks, and common tricks and practices that people use to effectively train these neural networks. Let's go through backpropagation first. When training neural networks, we want to learn how to correctly predict the outputs given the inputs, which means that we want to update the weights in each neuron in each layer to maximize the correctness of our model. So how do we do this effectively? Neural networks are trained using an algorithm called backpropagation. First, a training instance is fed through the neural network to make a prediction. We then measure how far our prediction is from the actual label. Next, we compute how much each neuron in the previous layer contributes to the output prediction. We iteratively do this for each layer. So for example, if we are up to layer 5, we compute how much each neuron in layer 4 contributes to the output error of layer 5. We want to repeat this process until we get up to the input layer. Finally, we perform gradient descent on all the weights, meaning we use the errors that we calculated to help us update the weights to increase the correctness of our model. We can then repeat this process for the data samples. When we finish going through all the data samples, we can perform backpropagation again and again until our model stops improving. Here's a nice visualization of what is happening. We can see that we are making a forward pass through the neural network, and when we reach the end, we make a backward pass to measure the errors contributed by each neuron in each layer. There are a few hyperparameters that are important to focus on when training neural networks. The first is the number of hidden layers. Deep neural networks are more efficient than shallow neural networks with the same number of parameters. Why would this be the case? Imagine you had to draw a forest. If you couldn't use copy and pasting, you would have to draw each tree, branch, leaf individually. In contrast, if you could draw one leaf, you can copy and paste the leaves to form branches, copy and paste the multiple branches to form a tree, and then copy and paste the tree to form a forest. Real-world data is often structured hierarchically, just like the forest example. Deep neural networks take advantage of this hierarchy because the deep neural networks learn low-level features in the lower-level layers, and the high-level layers combine the lower-level features to model high-level structures. Generally, it is a good idea to gradually increase hidden layers until the model starts overfitting. You can also change the number of neurons in each hidden layer. One common practice is to form a funnel with your neural network, where there are fewer and fewer neurons at each high-level layer. Another thing you can do is force each layer to have the same number of neurons, which reduces the amount of parameters that you have to change. Usually, it's a better use of your time to increase the number of layers than to change the number of neurons. Now, let's discuss some issues that you may face when training neural networks. One of the main challenges that people have faced when training deep neural networks is the vanishing and exploding gradient problem. During backpropagation, the gradients of the updates can get smaller and smaller to the point where the update step no longer changes the weights of the neural network and training will not converge. The other problem that you may face is the gradient can go larger and larger to the point where the weights become very large and the algorithm diverges. There has been a lot of research done to ensure that these gradient problems do not happen. One major innovation was the Xavier and Hay initialization, where weights are initialized according to a normal or uniform distribution that depends on both the input and output sizes. The researchers show that by using these initializations, the broad propagation algorithm is initially less likely to diverge. Another thing that helps reduce the gradient problems is using a non-saturating activation function for the hidden layers. A non-saturating function is a function that doesn't tend to have a zero gradient. One very common function is the Rayleigh activation function, or its variance, which should be used by default. The second major innovation that reduced the severity of vanishing / exploding gradient problem is batch normalization. Just before applying the activation function, we can perform batch normalization, which essentially zero centers the mean, normalizes the input, and then scales and shifts the results using 2 parameters per layer. Theoretically, this addresses the gradient problem by making sure that the variance of the signal in the layer is equal to the variance of the signal after the layer. And experimentally, batch normalization has been shown to decrease convergence time and improve performance for many different types of neural networks. And lastly, we will discuss some of the ways that we can further improve training. One thing that you can do when you have a small amount of data is to try transfer learning. This is simply where instead of training a neural network from scratch, you can find an existing neural network that accomplishes a similar task and then reuse the lower layers of that neural network. This makes it faster to train your neural network because your neural network will learn will not have to relearn from scratch. In addition, it can be a good idea to freeze the transfer weights, meaning we fix the weights so backpropagation does not change those weights. This makes it even faster for your neural network to train and converge. When you don't have a lot of labeled data, you can also try pre-training, which involves training your model on unlabeled data using an unsupervised neural network and then transferring those weights. We haven't gotten over any unsupervised neural networks yet, but we can discuss this later on. Similarly, you can also pre-train your model on a different task and then perform transfer training. Another way to improve training is by using a different optimizer. The simple optimizer is the typical gradient descent algorithm, but there are many other optimizers to choose from. We won't go over the different optimizers, but the optimizer that you should use by default and you should try first is the Atom optimizer. Here's a cool visualization on how the different optimizers help find the best weights. We can imagine the x-axis to be one weight and the y-axis to be another weight parameter, and the neural network tries to find the best x and y value to minimize some loss function. The lines in the background represents a contour map, where the bluer the line, the lower the value, and redder the line, the higher the loss function. And lastly, vectorization, or constraining the model, can help a lot with preventing overfitting. Some common techniques include early stopping, or stopping the training process early when our model stops improving, or L1 or L2 regularization, where we penalize large weight values to force our model weights to become smaller. We can also use the idea of dropout, where at each training step, each neuron has a probability of being unused. And data augmentation is where we create more data from the data we already have. This is a common practice in computer vision because we can easily make changes to our image without changing the label that we assign to the image. For example, we can rotate an image of a cat, which drastically changes the image but doesn't change the label. To summarize, we've gone over how we can effectively train deep neural networks. So we'll try to answer some of these conceptual questions.